All right, 10.5. Are you guys ready?
Yes.
10.5 has two different kinds of problems in it. One of the kinds of problems is going to be the complements idea, okay? And the other type of problem is going to relate to something we did ages ago back in chapter 2. All right, so the complements principle of counting, actually both pieces of this relate to what we did back in chapter 2. But the complements principle of counting is the more complicated of the two pieces. And I want to make sure that you actually have time to think about that on the day we do group work, which would be Monday for the complements principle. So that's the part I'm going to skip for now, okay? So we're going to do the easier of the two parts today so that we can do the harder part the same day that you do group work on it. Does that make sense? So I'm going to skip to the other half. They're not connected at all, so that's what we're going to do. So I want you to skip to problem, or the part that says additive principle. Okay, so the back half of this. All right, the additive principle of counting says that if I have two sets A and B, and I count the number of items in their union, this is the same thing as counting the items in A, counting the items in B, and subtracting their intersection. And we've seen that before this semester. I'll draw you a picture in a little bit. The second half of this says A and B are disjoint. Do you remember what disjoint means? Somebody said it. What did you say, Clinton? They're not connected. So if I were to draw like a Venn diagram, which is exactly what I'm going to draw in a minute, we draw a Venn diagram with two circles that didn't touch, right? So disjoint means not connected. So if we have something that does not intersect, and I were to try to use this formula, what would the number of items in their intersection be? 0. So that's why this formula right down here looks exactly the same, except it didn't have the part at the end, because it would be 0. So it's just not there. Guys, remember Venn diagrams? Some of you liked them, okay. Let's call this set A and let's call this set B, and let me remind you where this formula comes from because you've used it before. All right, this formula talks about counting the number of items in the union. So the union, do you remember what union means? That's intersection.
No, that's everything.
Union is all of everything combined, okay? So if I were to shade in the union, I would shade in all of the inside of both circles, right? They'd just be all a big, pretty shaded in picture. Now, that's great, but let's shade them in according to what's on the right-hand side of this equation. This says the number of items in A. So I'm going to shade all of circle A. And then the other one says that I'm going to shade all of circle B. And what happens when I do that? Yeah, the part where they overlapped was counted twice. It was a double count, wasn't it? So when I double count, I need to remove the double count exactly one time so that I don't have the duplication in it. And that's why you're seeing this subtraction of the intersection in this formula. You're not physically removing everything in the intersection, you're removing the double count. And in removing the double count, it would be in essence like me having done this, right? So there's nothing shaded twice now, and I really do have the union that I expected. Okay? So we're going to take a look at some problems, and I want to show you that these particular problems and the problems in the other half of what I'm going to do are very different. And they're very different by the way that the problem is worded. So this says, examples, if a single card is drawn from a 52-card deck, in how many ways can the following happen? So we're just talking about the description right now. I know we haven't talked about this section yet, but look at the first part of the description. Consider the 2,598,960 possible 5-card poker hands, and how many contain the following cards? Okay, ignoring the 2 million number here. What's the big difference between these two descriptions? Yep. I've got two problems. If you're looking at the packet, if you've printed it out, I want to look at the directions for examples 5 through 8 compared to the examples, or the directions for the examples 1 through 4. Okay, I want you to say that really loud, Tyler.
You're taking a single card in examples 5 through 8.
And what's going on over here?
You're looking for 5 cards.
Do you guys see that? That is a huge, huge difference. That difference is going to make or break you, okay? Because every time I've taught this before, people get confused about which one they're supposed to be using where, and it's not hard to tell. It really isn't. One's drawing one card out, and the other one's drawing a whole hand of 5 cards out, okay? So if you're drawing a single card out, which we are going to do in the examples we're working with right now, the process is very simple. These questions are really straightforward. There's no combinations. I don't have any multiplication. They're really straightforward, okay? The problems that we're going to do on Monday, the other half of this, they've got all that stuff in them. All the combinations and all the factorias and all of that stuff, because they're drawing out a 5-card hand, which makes things a lot more complicated, okay? So we're drawing out one single card. So let's take a look at that then. We're supposed to be drawing out a single card from the deck, and we want to know in how many ways could the following happen. And so we want a diamond or an ace. So let me write the language out the same way that the equation was written out before. I want the number of items that are a diamond or ace. And the word or is a union, right? You guys remember that? Or means union. So what this should do is this should count the number of diamonds plus the number of aces minus the number of ones that are diamonds and aces. Okay? So that's what I'm supposed to be doing. This is the only one I'm going to write out quite like that. But I'm counting everything in one category plus everything in the other category, and then removing the things that I overlapped when I counted. So, how many diamonds are there? There are 13 diamonds. How many aces are there? 4. And how many are both a diamond and an ace? 1. So why am I removing my ace of diamonds? Because I counted it twice, didn't I? I counted it when I counted the diamonds, and then I counted it a second time when I counted my aces. I don't want to count it twice. I've got to remove that double count. So I subtract off that double count, which was in this case the number 1. 13 plus 4 minus 1 is 16. Can you deal with that addition and subtraction? Yeah, you guys can. I know you can. Tyler's not so sure. Okay, we'll try again. All right, this one says a number card or a red card. Okay, so we got to count up the number cards. How many number cards are there? It's not 40. It's, what did you say? 9 per suit. And how did you get 9? Okay, so you started with the number 2 through 10. Okay, so 2 through 10 is 9 numbers. So there's 9 numbers in each suit. How many suits are there? 4. So I guess I lied a little bit. You're going to multiply right now. What's 9 times 4? 36. So there's 36 number cards, right? Okay. So you have 36 number cards. How many red cards are there? 26. We've already done this once before, right? We've talked about red cards versus black cards. So there's 26 red cards. And then I need to remove. What do I need to remove? The what? The red number cards, right? The cards that are both red and are numbered cards. How many red number cards are there? 18? Okay. I heard 2 different answers, so I was making sure I heard the right one first. 18. Where'd you get 18, Tyler? Half of 36. So the 36 were my number cards. So there's equal number of black and red number cards, so I just split it in half. That would be 18. So what is 36 plus 26 minus 18? 34? 45?
Yes,
Nobody's
it's
working
40.
with calculators today. It's 46? 44? Okay, I heard a couple 44s. 44 is what I have written down. Is it 44?
Yeah, it's what
Woo! We keep saying numbers. We're bound to hit the right one, right? Okay, it'd be better if we could just do it right the first time, though, yeah? All right. All right, let's try another one. A black card or a diamond. Every time I do this problem, I think I should go skiing. And for those of you who know what a black diamond is with your skiing, that means you know what skiing is. So, black diamonds. How many black cards are there?
6.
There's 36 black cards. How many diamonds are there?
There's only 26.
Oh, 26. I was just taking what your numbers were you gave me. 26. All right, 26. How many diamonds are there? 13. How many black diamonds are there? None. So you can either write 0 if you'd like, or just not write it at all, because this is actually the case where they're disjoint, right? There's no overlap between the diamonds because they are red and the black cards because they are not red. Okay? So we have 13 plus 26 to give me 39. Okay, we have one more. A black card or a club. How many black cards are there?
26.
26. We just did that, didn't we? How many clubs are there? 13. How many black clubs are there? 13. So it's still 26 cards, right? Yeah, so they definitely can still have this relationship where they could be completely contained inside of one another. Now, I want to make one comment. So in your group work and in your homework, when you do get to this section next time, one way to deal with this is exactly like what we did, where you're counting and you're removing something. A second way to deal with it, and some of you liked it when we did it before, would be to draw a Venn diagram. Now, on this particular example, what we did with the counting probably makes a lot more sense. I mean, like we can count up these numbers of cards pretty quickly. But on other examples, it may make more sense for you to draw a picture with a diagram for it, and that's fine too. So in drawing a picture with a diagram, it doesn't look exactly like you're using this formula, but you are. You just aren't sort of thinking about it as you're doing it. So if you want to use Venn diagrams, that is perfectly fine as well in this section. Okay? So we will finish this section next time.